Logical query processing order. In my opinion, this is the most important part of this course. Understanding the logical query processing order is crucial for writing efficient SQL queries. Unlike the way we read SQL statements from top to bottom, the database processes them in a specific sequence to retrieve the correct data efficiently. The logical execution order follows these steps. From, identifies the source of data and applies joins. Where, filters rows before any grouping occurs. Group by, groups the filtered data based on specified columns. Having, filters groups after aggregation. Select, determines what columns or expressions appear in the output. Distinct, removes duplicate rows if specified. Order by, sorts the final result set. Limit/offset, restricts the number of rows returned. Although SQL queries are written in a different order, understanding this logical flow helps optimize performance and avoid unexpected results. From. The from clause is the first step the database takes when processing a SQL select statement. It is like the foundation of a house, everything else builds on it. The from clause tells the database where to find the raw data you want to work with, whether it is a single table, multiple tables, or even a subquery. What does from do? It identifies the data source. The from clause specifies the tables or other data sources, like views or subqueries, that contain the data you are querying. Next, it pulls all the rows and columns from the specified source into a temporary working set that the database will refine in later steps, like where or select. Why is from processed first? The database needs to know what data it is dealing with before it can filter, group, or sort it. Without a starting point, the rest of the query, like where or group by, would not know what to act on. Think of it like going to a library. You first choose which bookshelf, table, to look at before searching for specific books, rows, or organizing them, like grouping or sorting. The from clause can include multiple tables using join operations. What happens in the from step? The database constructs the initial dataset by retrieving all rows and columns from the specified tables. If there are joins, combining rows from multiple tables based on the join conditions. If a subquery is used, executing it first to produce a temporary table for the outer query. This dataset is often called the result set or virtual table at this stage, and it is passed to the next step. No filtering, grouping, or column selection happens yet. From is just about gathering the raw data. For example, from users as u. Join orders as o on u.id equals o.user_id. Join products as p on o.product_id equals p.id. In this query, the from clause starts with the users table, assigns it an alias u, and then joins it to the orders and products tables. The on condition ensures that data is combined where relationships exist. This structure helps reduce redundancy and improve query efficiency. Common pitfalls. If you forget to specify a table in from, it will cause an error in most databases. If joining tables with columns of the same name, like ID in both products and orders, you must qualify them as products.id to avoid errors. Joining too many tables without filtering can lead to massive data sets, slowing down the query or crashing it. Join. The from clause is where the database gathers its raw data, and when we need to combine data from multiple tables, the join statement becomes the star of the show. A join allows us to link tables based on related columns, creating a single, unified dataset that the rest of the query can work with. But here is the key: when using joins, you have choices about where to apply filtering conditions. Those choices can make a big difference in both the results and the performance of your query. Let us explore how filtering works in join statements, focusing on two places where conditions can be applied: the on clause and the where clause. When combining tables with a join, you can filter rows in two distinct ways. On, this clause is part of the join itself and filters rows during the join process. It determines which rows from the join tables are paired together to form the temporary dataset that moves forward in the query. Think of on as a gatekeeper who decides which rows get to dance together before the rest of the query even starts. Where, covered later, this filters rows after the join is complete. It takes the full dataset produced by the from and join operations and trims it down based on your conditions, like a final quality check on the combined data. Select asterisk from users as u. Join orders as o on u.id equals o.user_id and o.status equals completed. Here is what is happening. The from clause starts by identifying the users and orders tables. The join combines them using the on condition u.id equals o.user_id, which matches each user to their orders. The additional condition o.status equals completed in the on clause means that only orders with a status of completed are included in the join. Any orders that are, say, pending or cancelled are excluded right away, before the joined dataset is even formed. The result: the temporary dataset contains only rows where a user has a completed order, with each row combining user and order details. The impact on large tables. When working with large data sets, placing filters inside on can significantly improve performance. By reducing the number of rows early in the process, the database engine has less data to handle during the join operation, which can speed up query execution. In contrast, filtering in where after the join may result in unnecessary processing of a much larger data set, leading to slower performance and higher resource usage. Just keep this in mind when creating select statements, especially when dealing with large tables. The impact on large tables. When working with large data sets, think millions of rows, the placement of filters becomes critical. Placing conditions inside the on clause can significantly boost performance because it narrows the dataset early in the query execution process. By reducing the number of rows during the join, the database engine has less data to process in subsequent steps, which can speed up query execution, sometimes dramatically. Reduce memory and CPU usage, making your database happier and more responsive. Avoid bottlenecks, especially in busy systems handling many queries at once. In contrast, filtering in where after the join means the database first creates a potentially massive temporary dataset, combining all rows that match the join condition before trimming it down. This can lead to slower performance, as the database processes unnecessary rows. Higher resource usage, which might strain your system. Longer wait times for users, especially in applications where speed is critical. For example, if your orders table has 10 million rows and only 5% are completed orders, filtering status equals completed in the on clause means the join only deals with 500,000 rows. Filtering in where forces the database to join all 10 million rows first, which could take much longer. Where. What does the where clause do? The where clause evaluates each row in the dataset produced by the from and join clauses, keeping only those that meet your specified conditions. It is like a bouncer at a club, checking every guest, row, against a list of criteria and only letting the qualified ones through to the next part of the query. This happens on a row-by-row basis, meaning where focuses on individual records, not grouped or aggregated data. Since the where clause is processed right after from and joins, it plays a huge role in query performance. By trimming the dataset before grouping, sorting, or calculations, where minimizes the number of rows the database has to handle, which speeds up execution, especially with large tables. Filtering out unnecessary rows early means less memory and CPU usage, making your database more responsive, particularly in systems handling thousands or millions of records. A well-written where clause makes your query's intent clear. It helps you, and others, understand exactly which data you are targeting. Example: where u.country equals USA, and p.category equals electronics, and o.order_date between January 1, 2023 and December 31, 2023. The where clause filters this dataset to include only rows where the user is from the USA. The product belongs to the electronics category. The order was placed in 2023. Only rows that satisfy all these conditions, combined with N, pass through to the select clause, which then picks the column's name, product_name, and order_date for the final output. By applying these filters early, the where clause ensures that the database does not waste time processing orders from other countries, non-electronic products, or orders outside 2023. This is like sorting through a huge pile of mail to keep only the letters addressed to a specific city before organizing them further. Unlike the having clause, which we cover later, where works on individual rows, not grouped or aggregated data. This means you cannot use aggregate functions like count or average in where, those belong in having because they require grouping first. The database processes where before group by, so it does not know the average, salary, yet. Instead, you use having after grouping. This distinction is crucial, as it is a common source of errors. To make your where clauses effective, consider these tips. Write conditions that eliminate as many irrelevant rows as possible. Use n, or, and parentheses to ensure your logic is clear. For example, where u.country equals USA or u.country equals Canada, and p.category equals electronics groups conditions correctly. When writing complex queries, add one where condition at a time and check the results to ensure you are filtering as expected. The impact on performance. Faster query execution, critical for real-time applications like e-commerce or analytics dashboards. Lower resource usage keeps your database server happy under heavy loads. Better user experience, as reports or apps load quicker. Without a where clause, or with a poorly designed one, the database might process millions of unnecessary rows, slowing everything down and potentially causing timeouts or crashes in extreme cases. After the from, join, and where clauses have gathered and filtered our dataset, the group by and having clauses step in to organize data into meaningful summaries and refine those summaries further. These clauses are essential when you want to analyze data by categories, like finding the total sales per customer or the average score per department. Let us dive into how group by and having work together to transform raw data into powerful insights, continuing our journey through the SQL select statement's logical processing order. The group by clause, summarizing data by categories. When we need to aggregate data, the group by clause is our go-to tool. It takes the rows from the dataset, already filtered by where, and organizes them into groups based on one or more specified columns. Each group represents rows that share the same values in those columns, like putting similar items into labeled bins. Once grouped, we can apply aggregate functions, such as count, sum, average, minimum, or maximum, to summarize each group into a single row of results. The having clause, filtering group data. While the where clause filters individual rows before grouping, the having clause is its counterpart for group data. It applies conditions to the groups created by group by, keeping only those groups that meet your criteria. Because having works after aggregation, it is the place to filter based on results of functions like count, sum, or average, something where cannot do since it runs earlier. Think of having as a quality control inspector who checks each group's summary stats and decides which groups make the final cut. It's processed after group by, ensuring you're filtering based on the aggregated results, not raw rows. Group by example. Select u.id, u.name, count, o.id, as order_count. From users as u. Join orders as o on u.id equals o.user_id. Group by u.id, u.name. Having count, o.id, greater than 1. The from and join clauses combine the users and orders tables, linking users to their orders. The group by u.id and u.name clause organizes the resulting rows into groups where each group contains all rows for a specific user, identified by u.id and u.name. For each group, the count o.id function calculates the number of orders, producing one row per user with their ID, name, and order count. The result might look like ID, name, order underscore count. 1 Alice, 3. 3, Charlie, 2. Each row represents a group, summarizing the user's orders. Why include u.name in group by? Because any column in the select clause that is not aggregated, like count, must appear in group by to tell the database how to group the data. This ensures each group is uniquely defined. Some databases are more lenient, but it is best practice to list all non-aggregated columns for clarity and compatibility. The having clause filters the grouped results, so only groups, users, with order underscore count greater than 1 are included. The group by clause is powerful because it lets us answer questions like: how many orders does each customer have? What is the total revenue per product category? What is the average score per student across classes? By grouping rows, we can summarize large data sets into concise, meaningful results, which is crucial for reports, analytics, and decision making. It is processed after where, so it works with a filtered data set, making it efficient by only grouping the rows we've already narrowed down. Practical tips for group by and having. In group by, include every column from select that is not part of an aggregate function, like u.id and u.name, to avoid errors in strict databases. Name aggregated columns clearly, like count, o.id, as order underscore count, to make results readable. Use where to reduce rows before group by for better performance. Since having filters groups, double-check your aggregate conditions to ensure you are not accidentally excluding valid groups. When learning, group by one column and use one aggregate function, then add complexity like multiple columns or having as you get comfortable. Both group by and having can be resource intensive with large data sets because they involve sorting and calculating aggregates. Imagine group by as a chef sorting ingredients into baskets by type, apples in one, oranges in another. For each basket, the chef calculates a summary, like total weight, sum, or number of items, count. Having is the chef's assistant who checks each basket and keeps only those meeting a rule, like baskets with more than 5 items. Together, they turn a chaotic pile of ingredients into a neat report, just like group by and having turn raw data into summarized results. A common group by mistake. When using group by, all selected columns must either be part of the grouping or included in an aggregate function. Otherwise, many databases will return an error. Select u.id, count, o.id. From users as u. Join orders as o on u.id equals o.user underscore id. Group by o.order underscore date. Since u.id is neither in group by, nor in an aggregate function, the database does not know how to handle it. Always ensure that every column in select is properly grouped or aggregated. The correct version has group by u.id as the last line. The group by has changed from o.order underscore date to u.id. Select. The select clause determines which columns or computed expressions appear in the output. The data returned can be raw table values, computed fields, or results from aggregate functions. Example. Select distinct u.id as user underscore id, o.order underscore date, p.product underscore name, count, u.id, as total underscore employees. Here, we use distinct to remove duplicate results. Assign an alias user underscore id for better readability. Include an aggregate function count u.id to count the total number of orders per user. Distinct. The distinct clause is used in a select statement to remove duplicate rows from the result set. It ensures that each row in the output is unique, based on the values of the columns specified in the select clause. Distinct is particularly useful when you want to retrieve unique values or combinations of values without repetition. Distinct applies to the entire row of selected columns, not individual columns. It considers the combination of all columns in the select clause, but using it with one column, like select distinct name, effectively gives unique values for that column. Distinct example. Select distinct u.id as user_id, o.order_date, p.product_name. This ensures that each user, order date, and product combination appears only once. While distinct can be helpful, it should be used carefully as it may impact performance. Distinct can be resource intensive, especially on large datasets or with many columns, as the database must compare entire rows to identify duplicates. Sometimes distinct is used to fix poorly written queries, like duplicates from incorrect joins. In cases like this, address the root cause, so fix the join condition, rather than relying on distinct. Some databases support distinct on, which allows you to keep the first row for each unique value of a specified column or expression. This is non-standard and not supported in most databases. The order by clause sorts the final result set based on one or more columns. By default, it sorts in ascending order, smallest to largest, but specifying descending reverses this. The order by clause operates on the result set after all filtering, grouping, and deduplication have been completed, ensuring that sorting is applied to the final output. Ascending order, the default, like A to Z, and 1 to 10. Descending order, like Z to A, and 10 to 1. Multiple columns can be specified, with sorting applied sequentially, first by the first column, then by the second, etc. Example. Order by O.order_date descending, P.price ascending. Here, O.order_date descending ensures the most recent orders appear first. P.price ascending sorts products by price in ascending order. Sorting improves readability and usability, especially when dealing with large result sets. But, sorting behavior varies when null values are present in a column. Some databases treat null as the highest value, placing nulls at the bottom when sorting ascending. Others treat null as the lowest value, meaning nulls appear first. To explicitly control this behavior, use nulls first or nulls last, if supported by your database. Order by price descending nulls last. This ensures that null values do not appear at the top when sorting by price. Sorting options. Sort by one column, as in order by name ascending. Sort by multiple columns, with precedence given to the first column listed. Order by city ascending, name descending sorts by city first, then name within each city. Sort by computed values, as in order by salary times 1.1 descending. Sort by column aliases defined in the select clause, like select count, o.id, as order_count. Order by order_count. Some databases allow sorting by column position in the select clause, like order by 1 for the first column. This is less readable and not universally supported. Some databases allow order by on columns not in select, as select name from users order by age, but this is not portable, it fails in SQL Server. Limit and offset. The limit clause is used in a select statement to restrict the number of rows returned in the result set. It is often paired with the offset clause to skip a specified number of rows before starting to return rows. These clauses are particularly useful for pagination, retrieving a subset of results like top n rows, or sampling data. The limit and offset clauses operate on the fully processed and sorted result set, determining which subset of rows to return. Limit is most meaningful when combined with order by, as it ensures predictable results. Without order by, the rows returned by limit are arbitrary and may vary. Limit example. Limit 10. This returns only the first 10 rows of the result set. When combined with offset, it allows pagination. What is pagination? Retrieve a specific page of results, like 10 rows per page for a web application. Offset. Used to skip rows, often for pagination. For example, to show the third page of 10 results. Limit 10 offset 20. This skips the first 20 rows and returns the next 10. It is a way to manage large datasets without overloading queries. SQL Server uses top for limiting rows, as in top 10, and offset fetch for pagination, like offset 10 rows fetch next 10 rows only. Some databases allow alternative syntax, like limit 10, 20, where 10 is the offset and 20 is the row count. Limit improves performance by reducing the number of rows returned to the client. However, large offset values can be slow, as the database must still process all skipped rows. If row_count exceeds the number of available rows, limit returns all available rows. If the result set is empty, limit returns no rows. Negative or zero limit values are invalid in most databases. Limit and offset are useful for pagination, but offset can become inefficient for large data sets. For example, select asterisk from orders. Order by order_date. Descending limit 10 offset 10,000. Only 10 rows are returned, but the database processes and discards the first 10,000 rows, which can slow things down. If possible, try something like this. Select asterisk from orders. Where order_date smaller than January 1, 2024. Order by order_date descending. Limit 10. This avoids scanning unnecessary rows. Since we are talking about limit and offset, here is a nice real-world example. When retrieving data from a database, sometimes you do not want to see all results at once, especially when there are many records. Instead, you might want to view them in pages, like when browsing products in an online store. Limit tells the database how many rows to return, or display. Offset tells the database how many rows to skip. On the slide you see an example of showing 10 records at a time. The first query gets the first 10 orders, offset 0, no rows are skipped. The second query skips the first 10 and returns the next 10. The third query skips the first 20 and returns the next 10. This is useful for pagination in apps, where users click next page to see more data. Mastering the SQL select statements processing order empowers you to write efficient, readable, and maintainable queries. Here is why it matters. Query optimization: apply filters, where, having, early to reduce unnecessary data processing, minimizing resource usage. Debugging: understand the logical flow to quickly pinpoint and resolve query issues. Performance tuning: structure queries strategically to enhance execution speed and reduce server workload. By following best practices, SQL queries can be made more efficient, readable, and maintainable. So, mastering SQL's logical execution order is key to writing powerful, optimized queries. Use aliases to improve query readability. Apply filters thoughtfully to optimize performance. Structure queries logically for clarity and maintainability. By leveraging the logical execution order, you can craft powerful SQL queries that deliver accurate results efficiently. Keep these principles in mind to elevate your SQL skills and produce high-performing, maintainable code. That wraps up this video on logical query processing order. In the next video, we will create a database and tables which we will use in later examples. I look forward to seeing you there.